Uh, Hi guys. As I told in my first video, I will be discussing more about this confidential transactions. And one of the papers that says more in detail about this is the ZK Ledger, as I told you in the last video. It's basically one of the things like the transactions has to be confidential and also it has to be auditable by the authorities. So this is basically this can be applicable for the bank related transactions between the banks when you transfer the money, how it can be audited in a proper way. So here actually the ZK ledger it's basically it is explaining much about the Pedersen commitments and NIZK, that is a non-interactive zero knowledge. So these are the things that it is using for achieving this confidential and auditable uh, transactions actually. So, so this is the basic architecture, basic diagram where it explains about how the banks communicate and how the trades can be done between the banks, which has to be very transparent and also which will avoid all sorts of problems that happens. Something like, let's say, Bank of America when it prints, it is transferring a amount of coins from or amount of money from Bank of America to JP Morgan, let's say. So then what happens is that whether the assets are there or not in a particular bank, how that can be verified. So for that only here the ZK ledger is using this commitments here, and the commitments are mostly, as you know, the Peterson commitments when we use it is encrypted. So there is a shared ledger that's been used, as you see here in the bottom, where each column is representing a particular bank. And when a transaction is transferred, let's say of $100, when it transfers from one bank to the another bank, here it gets deducted, and the Goldman Sachs will have the addition of that. So when it is being transferred from one account to the another account, it needs to be verified that in that account this asset is there or this much assets are at least there. So that will be verified here and that will be stored here. That means the commitment to that particular cash which has been transferred from BOA to the Goldman Sachs, that will be stored here. So the deduction, the commitment that is stored in the Bank of America is of the commitment that that particular coin has been deducted and the balance was there at that time, and the Goldman Sachs will get that amount, and that's the commitment that's been stored here. So this book basically an off-chain shared ledger, but in the on-chain part, when you store the states and all the details, you can use the commitment cache, because to speed up the process, that for what all transactions that is happening and what is storing here, that will be stored here in the form of commitment cache, which will improve and speedify the process. Because here when it comes to safety and the auditability, of course it works perfectly, but when the transactions are happening in a huge amount between the banks and when number of banks are involved in it, then the NIZK or the non-interactive zero knowledge proof, that will take more time. And for that to get reduced, actually you use the commitment cache. If you depend mostly on the off-chain ledgers part, then it will take more time to complete a transaction, even if it is a parallel transaction that's happening. But since the banks transfer the transactions in parallel, the transactions will be the number of what you say the time that is needed to execute this transaction will increase linearly. It's not going to be increasing like an quadratically or in a in a double mode of time. It will be mostly in the in a linear way to increase the transactions, because the thing is that we are also going to use the commitment cache here. So the commitment cache reduces the transfers that's happening between the banks. That's what the ZK Ledger paper says. So as you see, the auditor, it will be mostly an institution that will ask queries, and the queries are being responded from the commitment cache, and the commitment cache is getting filled timely from the off-chain ledger here. So the thing is that the verifier is the auditor, and here in this case the bank is the prover. So the prover answers to the verifier what all queries it has been asking. Something like, let's say, at point one, at a point instance of t, what is the number of euros that you have it, that can be set by summing up this particular rows here. So, I mean, not rows, but for Goldman Sachs or for JP Morgan, it will be like for a particular column, it will be summed up. And for that particular instance, what all commitments you have stored there, that will be summed up because it is additively homomorphic. As we are using the Pedersen commitment, it is where you can add all those encrypted data what you're storing it here for that particular instance. So you can sum up, you can do a what you say product of those all the columns here, and you will get the answer, and that will be passed on to the auditor. So the thing is that here the main thing is like the commitments which are stored on top of that, we will be able to add, and also we will be able to do the multiplication operations on top of encrypted data. So that's the basic thing, and that improvises the security and also helps the auditing institutions to audit the data for a particular instance at any point of time. So that's the basic thing here. That's what this paper explains, and you can see that this is based on the Go prototype. Actually, the ZK Ledger has run that, and this is the benchmark that it's been generated. Like for number of K banks, this is the commitment, and this is the amount of time it has taken to create, and also this is the time it has taken to verify it, and this is the range proof. And range proof, when it comes to the range proofs, actually it means that for a particular transaction, actually you need to have the range proof, because for n minus 1 times, actually for that the value should not go between more than that particular 0 to n minus 1, and that is the range. And for that you need to generate a range proof for that. So the commitment proof in a transaction, the consistency, which means the proof of consistency has to be generated, where this I will be telling you in the coming slides. And the consistency proof, the distinctive, and the range proofs have to be generated for that number of K banks. And as you see, the number of milliseconds that increases is basically for the range proof, because range proof takes a good amount of time and it is very expensive when it comes to the generating a range proof. And range proof is very important also, because it helps to verify that the values that's been added in the transactions are coming up in that particular range. So the size is also very much huge. And as you see, this is the performance, and you can analyze the things here. The x-axis is basically the number of banks that's involved in the transactions. That means that instead of having a transfer from one bank to another bank, you can include multiple banks to participate in that particular transaction. So like X amount of coins or X amount of dollars will be transferred from one bank to another bank, and then from that bank to another bank. So likewise, there will be multiple banks that will be involved. And as the number of banks are involved here, you can see that the transaction time, how it increases as we go. And you can see here the verify one, create one, it means that you're using a 1-core CPU. And with 12, that means that you're using a 12-core CPU. So when you have a 12-core CPU, of course, the number of milliseconds or the number of time, the throughput will be very good enough, and that means that number of transactions will be executed in a much more optimized way compared to the 1-core CPU. So that's the difference that is being it is showing here. But anyways with number of banks, as you increase the anyways with the 12 core CPO 12 core processors also, this will increase. And the same thing with the complete transactions here, like as you are when you say the complete transactions, that means that you are creating a transaction, you are doing and generating a proof for all those things like commitments and everything, and then after that you are doing the verification for all these transactions. When you combine it, this is the time that it is taking to generate it for number of banks. uh, and the same thing here, like this is basically the throughput where all banks transacting and one bank transacting here, that you can check it out here. Like with a one bank transaction, like as as the banks are transacting parallelly, you can see how it works here, and with one bank transacting how it is working, that you can see, like it's about the parallel transactions that's happening. So at a time when you have parallel transactions that's happening here, you can see that the throughput is very what do you say, the very minimal, or it is giving you an maximum efficiency here. But with single transaction, it is decreasing the performance. That means the throughput is very minimal here. So it's always like all banks, if it is transacting in parallel, the throughput will be very optimal. This is also not just with the transactions. That means that from bank A to bank B in the previous step, these all were showing those things, like the dollars were transferring from one bank to the another bank. But you can audit it also when you bring the auditing part here, like how much time it takes for uh, audit to happen. And when I say online and offline audit, it means this one, like for an online audit, when you are in blockchain and when you are using a commitment cache, that means that you are it is increasing the speed, and it reduces the what do you say, that number of time it takes to complete that audit, that is like asking questions and responding to that. But when it comes to the off-chain, you are not using the commitment cache, but you are using only the off-chain cache, which is the shared ledger between the banks. That will take more time. So that's the difference that you can see here in this diagram, where the transactions in ledgers, when it is huge, then the auditing time, it varies accordingly. But it is not showing that much, because in offline audit it is increasing linearly, because you are using a shared ledger, and that's the basic difference here. So that's what this graph shows. Yeah. And next thing is that when I say about structure of ZK ledger, it means that what all fields have to be stored in a table, in an off-chain table. That means what you see here, that's been explained there. We can check it up. Of course, the timestamp has to be there, and apart from that, you will need the commitments for each transaction that is happening, and also the proofs. That proofs, when I say it's about the transaction commitments, are basically the Pedersen commitments, and the proofs, it is using the non-interactive zero knowledge proof. So that's part of the structure. But the proofs are of three different types. One is of the proof of balance. It means that there are two invariants to this. When I say two invariants, it means that when a coin, or when a currency is being transferred from one account to the another account, it means that you can only transfer it, you can't create it, or you can't destroy it. So that's one of the rules that has to be placed. And another one thing is, and for that to check it and that to be verified, you are using a proof of balance. And then you have a proof of assets there. The proof of assets is something like when you're transferring the assets from one bank to the another bank, it means that it should be present in the sender's account, otherwise it should not be transferred. So for that, you need to generate the proof, and for that you have the proof of assets that's been stored here. And then the next one, I think it is of the proof of consistency, which means that the audit tokens which is being created and the commitments which is stored here in the Pedersen commitment, there you use the random input, and that has to be same, or else then there will be no consistency in the tokens. So that's, and for that you use the proof of consistency. So so actually there are five fields apart from the timestamps, that which is the Pedersen commitment, the audit token. Audit token, it is basically like, when an auditor requests a particular, sends a particular request, there should be an identifier number or a serial number which is has to be unique, and it uses the random input to generate that audit token. And basically the thing is that, yes, you use an audit token here, and that's one of the field, and then rest of the things are like the all the three proofs, which makes the commitment as consistent as possible. So that's the structure of this. Of course, the ZK ledger, what we use, it's basically the use cases. At least these are the, you know, basically for the four use cases that they say, like the financial leverage, which means that, like there should not be much frauds that should happen. Then this solves that particular thing because of the shared ledger between the banks and also the commitments. So the since it is a commitment that is stored, it is not readable within a naked eye, but it is summable, and also it can be multiplied because of the additive homomorphic properties of it. You will be able to perform the additive homomorphic operations in that. And next one is the asset illiquidity. There will not be an illiquid assets. That means that the assets whichever it's there in the account, only those accounts can be transferred. It's not like if the assets are not there, they can mint it and then, or they can create it and then they transfer it. That's not possible because of the proofs that's been stored. And with this, the counterparty risk exposures and market concentration, these are also the other fields that is very useful if we use the ZK ledger. So this is what I would like to say in this video, but in the next coming videos, I think I will be explaining more about the Pedersen commitments and the non-interactive zero knowledge proofs that will be used, and that's basically the main thing about this confidential transactions. So yeah, thank you for watching.